So chapter 18, we're looking at more equilibrium. Good news, same math, products over reactants. Boom, got it. We're just going to be applying it to a very specific class of chemical reactions. Here we're actually looking at our acid and base chemistry. And we've seen acids and bases before, but now armed with what we know about equilibrium, we can be a little more specific as to what's going on. So quick definitions. Feel free to pause, get them, and then we'll talk through these. But there's really three definitions that we're going to be responsible for knowing. One of them you already got. Arrhenius, we've heard his name quite a bit with the modified Arrhenius equation. Here's his work with acids and bases. So this is the one you know. When you look at a compound and say, is this an acid, is this a base? We currently know that as the Arrhenius definition, where we say that an acid is a compound that gives off an H plus ion or a proton when it dissociates in water. That would then get picked up by the water. So the H plus actually gets picked up by the water to form what we call hydronium. Those are essentially referring to the same particle. So H plus in water forms this hydronium, H3O plus. They are synonymous. And then a base, we know, is any compound that donates a hydroxide or OH minus ion into solution. And so when we're looking kind of our base naming systems, we said if it starts with an H, it's an acid. If it starts with an OH, it's a base. That is our Arrhenius definition. And so we've seen these before, but if you remember, we said there's strong and there's weak. Now that we know about equilibrium, we can say, okay, how weak is it? Let's give it a number to describe how weak that acid actually is. More on that to come, but that's kind of why we're kind of layering in this equilibrium part for our acids and our bases. So you know the Arrhenius already. Then the first kind of new set of definitions is our Bronsted-Lowry definitions. And so this is looking at kind of a specific type of reaction where we have multiple species that have an H or a hydrogen. We got to keep track of which one's acting as an acid and which one's acting as a base. Now, the good news is our acid definition is the same as our Arrhenius. We say that our Bronsted-Lowry acid is the one that gives off the H plus. The difference in definitions is our base, our Bronsted-Lowry base, is just going to accept that H plus. And we're going to look at some examples here, but that's kind of the big difference in the definition there. We're just saying who's given the H and who's taking the H in terms of describing our particles. Then our last example here, which we're going to touch on briefly, but worth noting while we're talking about our other definitions, is our Lewis definition. And Lewis dot structures and our Lewis structures for geometry and molecular shapes. Lewis was all about the electrons. And so Lewis is like, well, we got substances that don't have any H's that still are corrosive. How can that be? And so he was looking at it from the electron kind of angle or electron side. He says a compound or an atom or an ion that is accepting electrons is the Lewis acid. The one that's giving the electrons is the Lewis base. Now, good news, the charge still changes in the same way. So for example, if you donate an H plus, you become more negative. If you accept electrons, you become more negative. So our acid is always going to become more negative. Our base then is becoming more positive, if that helps you keep track of our different definitions. Cool, just a couple examples to start thinking about our different definitions here. So Arrhenius acid gives off an H in solution, gives off that H in solution. Our bases give off the hydroxide in solution when they split apart. We know that one. We've seen that one before. Again, if you want to pause it, that's fine. But this one, pretty straightforward. The new one, though, is our Bronsted-Lowry definition. So here we've got, if you're looking at our first example here we got two things that both have a hydrogen. Well, okay. Which one's the acid? We would have to look to see which one's losing its H. We tend to think of these in pairs. So if you think about your hydrochloric, it's changing into the chlorine, or the chloride, excuse me. Our water is changing into the hydronium. And so if you're thinking about your pair, HCl is turning into Cl minus. Well, that's going to give away or lose its H. It's the acid. This water is gaining the H. So here it is acting as the base. The H donor is the acid. The acceptor is the base. But it's kind of like playing practice field, right? You got the practice jersey. If you hand off the practice jersey to somebody else and they put it on, you switch teams. So you'll notice that our acid becomes what's called the conjugate base. This chloride ion is now more negative. It's now more like a base. And this base that accepted the H has now joined the acid team. It's now the conjugate acid. And so when we're thinking about kind of these partner pairs, it's nice to think about, well, which team are we on now? now that we've lost an H or gained said H proton. Here we get another reaction for you. And so this is where we start to see some of these weird analogies or weird examples. We got two things. Well, which one's the acid, which one's base? Let's see who's gaining or losing the hydrogen. If we're looking, our water is going to OH minus. It's got to lose a hydrogen to do that. So this is our acid. The NH3 is turning into NH4. So this NH3 is gaining the H. It's acting as the proton acceptor. It's the base. When it gains it, it becomes the conjugate acid. When the water loses its hydrogen, it becomes the conjugate base. And so thinking about these partner pairs, a little bit of definitions, more examples. It's nice to kind of think about why we would have these other definitions for something we already have a definition for. Cool. Some more pairs here, just to think about some examples. So our acid is going to turn into the conjugate base. Our base is going to turn into our conjugate acid. They come in partner pairs. And so we can look at some more examples here. So if we're looking at this example, pause it, give it a shot. If we're looking at our HF, our hydrofluoric is turning into fluoride. So this would be your acid. The water is accepting it. So this is your base. But when they actually change, this fluoride now has become the conjugate base. The H3O plus is now the conjugate acid. Here, try another one for me real quick. We've got our hydrogen being lost here. So we've got our acid turning into a conjugate base. This cyanide ion is accepting the hydrogen, changing into our hydrocyanide gas. This is our base, changing into our conjugate acid. One more for you, just for good measure. We've got NH4 plus going to NH3. This is losing its H. The CO3 2 minus the carbonate is going to bicarbonate. Here's our base, changing into conjugate acid. I'm going to skip this last one. Try it if you want. Oh, there's a bunch of these. Whole buckets. Cool. If we want to think about this in terms of its particles, here's our HCl. We've got our chlorine here. We've got our hydrogen here. We've got our water molecule here. What's really happening is we're binding our lone pairs, or what are attracting that hydrogen, and then we form this hydronium ion. So this is why we actually see the transfer of our hydrogens. One more example for you here. We got our water molecule and our NH3. We've got our lone pairs attracting that hydrogen, pulling it off to form our ammonium ion and our hydroxide ion. So if we're thinking about our pairs, NH3 became NH4 plus. This was the base accepting the hydrogen. This was the acid giving it away. And then they changed teams. Here's our conjugate acid and conjugate base. Cool. So just, again, think about these in terms of their pairs. When you gain or lose, you switch teams. That's what that kind of conjugate pair means for us. Here we had HCO3, went to H2CO3. This was acting as a base, accepting the hydrogen. The water lost it, so it was the acid giving it away. Changes into conjugate base and conjugate acid. Cool, some practice here. I'm gonna leave that for you guys. Feel free to check it on the PowerPoint. Boop. Real quick, Lewis. I want to talk Lewis while we're here, and I've got you. Lewis is all about our electrons. And so our Lewis acid is going to accept lone pairs of electrons. Our Lewis base is going to try to donate them. Vocab term here is what we call our adduct. Adduct, because you're adding them together. Typically, we're looking for our Lewis acid, we're looking for somebody who doesn't have a full octet. That's the species that's going to have room to accept more electrons. If you're looking at your fluoride ion, it's full. There's no more room for electrons around that fluoride ion, so it's going to have to be the base to donate them. In terms of our reaction here, watch out for the boron. Both the AP and the UMKC final really like to ask this question. Boron trifluoride is not a stable octet. It's got a lone pair space. It's got a lone pair void, if you will, that we could actually accept more electrons to form what we call our adduct, our final kind of product altogether. If we're thinking about our ammonia, got the lone pairs here. They can be donated, given to just the H plus to form our now ammonium adduct. So again, oh, but wait, we saw this with our other examples. Ooh, more on that to come, because turns out multiple definitions can apply to similar reactions. Don't worry about that. Want to talk through these kind of definitions? Make sure you've got them. See some good examples. Coming back, we're going to start to use these and start to think about pH and how this all fits into our equilibrium.